Let's take a look at this question now. We know that in order to find the acceleration, we have to analyze the entire system because it's the acceleration of the system. So let's do that now. Let's pretend the 20 and the 15 are one object. Okay, it's a 35 kilogram object. Okay, forget about the internal forces, doesn't matter. And there's essentially one force of friction acting on it that would have a value of 175. We're going to say the net force is equal to the sum of the forces. It's going to be FA plus FF1 plus FF2, or you could simply say FA plus FF, the force of friction, and then just combine them. The net force is also equal to the mass times the acceleration, m times a. Now we start plugging some numbers in. The mass here that we use is going to be 35 kilograms because when we're analyzing the whole system, we need to use the whole mass. The acceleration is what we're looking for, at least in the first part of the question here. FA is going to be negative 200 because it's to the left. FF1 is positive 100 because it's to the right. And FF2 is positive 75 newtons because it's to the right. Neg 200 plus 100 plus 75 gives me negative 25. It becomes 35 times A equals, sorry, I made a mistake here. It's not a major mistake because, in fact, I made two mistakes. I made a couple of mistakes, actually. The two mistakes end up kind of canceling each other out almost. Okay, my 200 newtons should be a positive value. My 100 newtons should be a negative, and my 75 should be a negative. So that doesn't give me a negative 25 newtons. That gives me a positive 25 newtons. A ends up being equal to 25 divided by 35, which is 0.71? Okay. Yeah, I think you're right, actually, yeah. 0.71 meters per second squared. How many people got that? Good, good. Yeah, that's the first step, and that's probably the most important step, because if you don't get that, you can't get the rest of it. Now, when we want to find the force between 1 and 2, whether we're looking for F12 or F21, doesn't really matter here. We got to analyze one of the objects. Pick one of them. I'll pick object number 1. There's no real good reason why I'm picking number 1 over number 2, but it works just because. Hey, just because. So we have an applied force here of 200 newtons that acts on that. If we're analyzing number 2, there wouldn't be an applied force of 200 newtons because it's not acting directly on number 2. It's only pushing on number 1, which it's number 1 that pushes on number 2, not the applied force. Okay, we have a force of friction that acts backwards here. It's 100 newtons. FF1 is 100 newtons. And we also have a force of 2 acting on number 1. If we were drawing the free body diagram for the other one, it would look something like this. Okay, 15 kilograms, we would have a force of 1 pushing on number 2. We would have a force of friction acting backwards of 75 newtons. And that would be it, besides the normal force and the force of gravity to cancel. Both ways should give us the right answer, though. We mentioned this the other day. If you have time, do it both ways. And if you get the same answer, then you must be right. All right, here we say the net force is equal to the sum of the forces FA plus FF1 plus F21, m times A. What mass do we use here? 20, 15, or 35? When we're analyzing the whole thing, we use the whole mass. If we're analyzing only object 1, then we use only the mass of object 1. It's 20 kilograms. The acceleration will be 0.71, because if the whole thing accelerates at that rate, then each of the individual objects must also accelerate at that rate. The applied force is 200 newtons here. It's positive. FF1 is negative 100. Plus F21. 20 times 0.71 is going to give me 14.2. 200 plus negative 100 is 100. Let's take that 100 over by subtracting. F21 is going to equal negative 86 newtons. How many people got negative 86 newtons? How many people got positive 86 newtons? Okay, if you got positive 86 newtons, I'm going to take a wild stab at this, but I'm guessing it's because you drew the 15 kilogram object instead of the 20 kilogram object. Is that right? Okay, which is good, which is correct. Okay, so technically, 2 digits. No, it's 2 digits. Technically, I was looking for the force of 1 on 2. I got the force of 2 on 1. So technically, the answer would actually be pos 86, because I didn't solve for what I was looking for. I got the force of 1 on 2. Sorry, the force of 2 on 1, not the force of 1 on 2. Okay, if I wanted the force of 1 on 2, it would be positive 86 instead of negative 86. But if you said negative 86 on tomorrow's quiz, then I'd mark that right. Okay, I'm not going to lose any sleep over the direction of that. Okay? So how many people would have got 100% on the quiz today if we had have actually had that quiz on that? Okay, good. Good. Tomorrow we should get more than that, get 100%, because we know exactly what to expect, and we've gone through another example here. Okay? If you're struggling with this, make sure you see me during scheduled help so that we can go over this and do well on tomorrow's quiz. All right, let's move forward here to some more problems, okay? You're going to see over the next few days that we're going to work on problems that are all more or less what we've already done. It's just different contexts. Today we're going to start off with more multi-force problems, more problems involving several forces acting at once, but specifically those problems are going to involve, at least to start off today, are going to involve elevators. Okay, we've all been on an elevator before. We all know that there's more than one force acting on you as you're in an elevator. We know that, first of all, there's gravity acting down on you. We know that there's a normal force acting up on you. For the first time, though, the normal force will not be equal to gravity for us. Okay, for the first time, we're going to find a situation where the normal force is either less than gravity or more than gravity. Remember all the questions we've done so far? We've said we can always assume so far that the force of gravity, m times g, is equal to the normal force. And it has been. We haven't been lying to you about that. In all the questions we've done so far, that has been the case. But now that's not going to be the case. Let's do a problem where we have a 73 kilogram man standing on an elevator that accelerates downward at 2.0 meters per second squared. Here's the elevator floor. Here's the man standing on the elevator floor, and he's accelerating downward at 2.0. So we're going to make it negative 2.0 meters per second squared. There's a whole bunch of things that we want to find, but before we even tackle any of those things, we want to get a free body diagram drawn. Now, pay really close attention to this. Don't even write this down quite yet, okay? I want you to write this down, obviously, but just drop your pens right now and watch for a second. There is a force of gravity acting down. By the way, the mass is also 73 kilograms. There's a force of gravity acting down. Now, there's also a normal force acting up. The force of the elevator floor is pushing up on the guy, right? But I'm telling you in this case that the force of the elevator floor, the normal force, isn't going to be the same as gravity. Is it going to be bigger than gravity or smaller than gravity? And how do you know? Travis? Travis says it's going to be smaller than gravity. Rucker, you had your hand up as well. Do you think it's going to be smaller or bigger? Okay, you think it's going to be smaller as well? Okay. Why, Travis, do you think the normal force is going to be smaller than gravity here? Okay, gravity always pulls us down though, right? In all the questions we've done until this point, gravity has been the same as the normal force. Laura's your hand up? Okay. Okay, the elevator is going down, but sometimes the elevator could be going down and the normal force could still be bigger. In this case, it's not. Okay, in this case, Rutger and Travis are absolutely right. But it's not always smaller just because it's going downwards. Okay. It does, yeah. You're going up in an elevator. I think I know what you mean by that, at least. You go up in an elevator. You guys notice this sometimes when you're going in an elevator, especially one that goes to, you know, a 50-story building or a 60-story building where the elevator needs to be fast. Okay, when that elevator starts moving, you feel like your stomach is in your shoes, right? When you start accelerating upward. You feel heavy. Why do you feel heavy? Well, in order to accelerate upwards, the normal force has to push up on you more than gravity. Let's think about that. If you're at rest on the ground floor, floor number 1, and gravity is equal to the normal force, then what's going to happen to you? The forces are going to balance, and you're going to stay where you are. You're not going anywhere, right? In order to go upwards, the normal force has to be bigger than gravity. That's why you feel heavier, because remember we said the normal force is how heavy you feel. Normal force is bigger than gravity. You feel heavier. But when you're accelerating downwards, not moving downwards, but accelerating downwards, okay, good. Accelerating downwards, well, then gravity has to be bigger than the normal force. There's an unbalanced force here. Otherwise, you wouldn't accelerate. And if that unbalanced force is acting downwards, then you're going to accelerate downwards. If it's acting upwards, you're going to accelerate upwards. In this case, we're accelerating downwards. The unbalanced force must be acting downwards. And since gravity is the only force that's acting down, it's got to be bigger than the normal force. So that's the way we've got it drawn. Now, we want to find the force of the elevator floor pushing up on him. What are we really looking for in question A there? The force of the elevator floor. What variable in this free body diagram am I solving for? Fraser? Good. The normal force is the force of the elevator floor. So let's get that. I'll give you a chance to write this whole thing down in a moment here, okay? Let's get this. Let's say the net force is equal to the sum of those forces. That's Fn. Don't get those two mixed up. Net force is the total force. Fn is the normal force. Two different things. It's equal to Fn plus Fg. M times A, should save some more room for this, M times A is equal to Fn plus Fg. Now the mass here is 73 kilograms. The acceleration is negative 2.0. We're solving for the normal force. And gravity is 73 times negative 9.81. Negative because it's acting downwards. 73 times negative 2 is negative 146. On the left-hand side, we've got, what is that, 73 times 9.81 is? 16.13, which we're going to take over to the other side by adding, what do we get when we add that to negative 146? Negative 146 plus 716 is somewhere around 580-ish, some 570.13, or 5.7 times 10 to the 2 newtons. The force of gravity we just found was 716. The normal force we just found was 570. The normal force was smaller. Should it have been smaller? Yeah, we established that when we drew our free body diagram that it should have been smaller because we're accelerating downward. When you accelerate downward, you guys have all experienced this before too, whether it's in an elevator or, you know, a drop ride at an amusement park, or you feel like your throat goes into your, or your stomach goes into your throat, right? Why? Because the normal force acting on you is smaller than the force of gravity. You feel lighter than you really are. We already found the actual weight, didn't we? The actual weight is the force of gravity. We found that to be 716.13 newtons, or 7.2 times 10 to the 2 newtons. The actual weight is how heavy you really are, and that's going to be your force of gravity. Now, the normal force acting on the man is what? We've done it. The force of the floor is the normal force. It's 5.7 times 10 to the 2 newtons. How heavy does the guy feel? What's his apparent weight? How heavy does he feel in this elevator? What is it? 5.7 times 10 to the 2 newtons. He really is 7.2 times 10 to the 2 newtons, but he feels like he's 5.7 times 10 to the 2. Your apparent weight, how heavy you feel, is your normal force. Remember we talked about that a week or so ago. So although it looks like there's a lot of work to do in this question, there really isn't. There's one free body diagram to draw. Solve for the normal force, and we're pretty much done. Okay, I gave you a chance to copy that out here now if you haven't already. Let's try one more example question. You don't have to copy this one, the question at least, down because it's in your textbook, but I do want you to copy the solution out. So it says a person and an elevator have a combined mass of 600 kilograms. The elevator cable exerts a force of 6,500 newtons up on the elevator. What's the acceleration of the person? So notice in the last question, we're analyzing the person in the elevator, not the elevator itself, just the person inside the elevator. In this question, we're analyzing the elevator itself. So let's draw a picture of that. Here's the person in the elevator. They have a combined mass of 600 kilograms. There's a force of the cable exerting a force of 6,500 newtons upwards. We'll call that F. What do you want to call that? F? Sorry? F1? We could call it Fn if we wanted to. It's like a normal force, right? It's not a floor pushing up, but it's a cable pulling up. It's like a normal force. We'll call it F1 here. It doesn't matter. 6.50 times 10 to the 3 newtons. There is a force of gravity acting now on this person, or on this elevator. It's acting downwards. But we don't know how big it is. Okay? We know it's 600 times 9.81, and we could figure out what its value is. But without doing that calculation, we don't know. And when we're drawing a free body diagram, it's not required that we do any calculations first. So let's draw a force of gravity down. Okay, we don't know whether it should be bigger or smaller than the force upwards. We just know that it should be opposite in direction. If the force of gravity is bigger than F1, the force of the cable, then what's going to happen to this elevator? It's going to accelerate downward. If the force of gravity is smaller than the force of the cable, then what's going to happen? It's going to accelerate upwards, right? Let's figure out what it is here. Let's say the net force is equal to the sum of the forces, F1 plus Fg. By the way, if Fg was equal to the force of the cable pulling up, what would happen? Nothing. It wouldn't accelerate at all, right? F1 plus Fg again. The mass here this time is 600 kilograms. We're using the mass of the guy and the elevator because we're not trying to find the force of the floor pushing up on the person. We're trying to find the acceleration of the elevator itself. F1 is positive 6,500, 6.5 times 10 to the 3 newtons. And the force of gravity is 600 times negative 9.81, negative because it's downwards. I think 600 times 9.81 is 5886. $6,500 minus 5886 gives me 614, and it's positive. A is equal to 614 over 600, which is somewhere around 1.1. Is that right? Somebody figured that out. 614 over 600. 1.02. Okay, so we're going to say 1.02 meters per second squared. It's a positive value. What does it tell us? Which way does it accelerate? Lane, which way does it accelerate? Good, it accelerates upward. And it should accelerate upward because we can see right here that we have a normal force that's bigger than the force of gravity. Are you going to feel lighter or heavier than you really are here? You're going to feel heavier. That's when your stomach is going to be in your toes as opposed to your stomach being in your throat, right? You're accelerating upwards, you're going to feel heavier. Now, we weren't looking for the normal force here acting on the guy inside the elevator, but if we were, we would have found that the normal force on that guy was bigger than the force of gravity on that guy. His apparent weight, in other words, is bigger than his actual weight. Nothing new here, right? Nothing new at all. In fact, I would suggest that these are probably even easier questions that we've been working on over the last couple of days. It's just more of the same thing of multi-force problems. And as I say, we're going to work on that for the next couple of days, just different scenarios kind of within that. All right, let's take a look at these two questions on 152 that obviously go along with that example question we just did. See what you can do with those, and then in about 6 or 7 minutes, we'll take a look at them as a group here, okay? Let's take a look at question number 2, everyone. It says, an electric chain hoist in a garage exerts a force of 2,850 newtons up on an engine to remove it from a car. The acceleration of the engine is 1.5 meters per second squared up. What's the mass of the engine? This is like an elevator problem, right? We don't have a guy inside an elevator like we have in the last couple of questions we've done. We've got an engine that's being pulled upwards, which is the same thing. So let's draw a free body diagram for this. Here's the engine. Okay, here's the engine. We don't know what its mass is. In fact, that's what we want to find, the mass here. We do know that we have a chain hoisting it upwards, though. We'll call that F1, or whatever you want. FC for the force of the chain, Fn for the normal force. Okay, it doesn't matter what you call it. Bottom line is its value is 2.85 times 10 to the 3 newtons, and it is upwards. Now, there is a force of gravity acting downwards as well. And we know that force of gravity is going to be smaller than the force of the chain. Can anybody tell me why I knew the force of gravity would be smaller than the force of the chain here? You know, if you didn't recognize that, it's not the biggest deal in the world, because in the end, you'd still be able to solve this correctly, even if you didn't see that the force of the chain was bigger than the force of gravity. But while we're trying to do everything correctly, if we spot that Fg is smaller, then we should draw it smaller. Why is it smaller? Why is the force of gravity smaller than the force of the chain? How do we know that? It's accelerating upwards. If it's accelerating upward, then the upward force must be bigger than the downward force. So I've got it drawn here so that the force of gravity is smaller than the normal force, or the force of the chain. And I know that I'm right with that. We're going to calculate its value, and if we get a value that's bigger than the normal force or the force of the chain, then we know that we've done it wrong. So let's analyze it now. This one's a little bit tricky because of the variable we're solving for here. F net is equal to F1 plus Fg. Let's say F net is equal to the mass times acceleration, which is equal to F1 plus Fg. Mass, we don't know. The acceleration is 1.5. Gravity is m times negative 9.81. Well, that looks a little ugly, right? Mass is unknown, but it appears in 2 places in that equation. So what do? Let's simplify it a little bit first. Say 1.5 m equals 2850, subtract 9.81 m. Here's a question for you. What's 1 plus 2? I think we can all get this one, right? What's 1 plus 2? We're struggling a little bit, but I think we all know that it's 3. 1 plus 2 is 3. All right. What's 1 apple plus 2 apples? Okay, you got 1 apple over here, you got 2 apples over here, you want to add them together, what do you get? 3 apples, right? You get 3 apples. All right. Then what's 1m plus 2m? If 1 plus 2 is 3, and 1 apple plus 2 apples is 3 apples, then 1m plus 2m is 3m, right? If 1m plus 2m is 3m, then 1.5m plus 9.81m, which is what we're going to have because we're going to take that over to the other side by adding, is going to equal 11.31m. Does that make sense? I've just taken the one term that has m in it on the right-hand side over to the left side so that we can combine those like terms. 1.5m plus 9.81m is 1.5 plus 9.81, 11.31 times m. Now we want to find the value of m. 2850 divided by 11.31 gives me 252 kilograms. How many people got that? Okay. How many people just hadn't quite had a chance to finish that? They were working on it, but just hadn't quite finished it. Okay. It's a tough one. It's a tough one because we're not usually asked to solve for a variable that appears in more than one place in the same equation. Yep. Yep. All right. Let's take a look at another one then. You guys are doing okay with these? 3.8 on 152. This is a skydiver. Again, it's not an elevator, but it's kind of like an elevator. We got a force of gravity pulling down on the skydiver and then a force pushing up, just not the force of the elevator floor pushing up, that's all. Skydiver is jumping out of an airplane. During the first few seconds of one jump, the parachute is unopened. The magnitude of the air resistance acting on the skydiver is 250 newtons. The force of air resistance, that's going to act up, right? Because as you fall, gravity pulls down, air resistance has to push up on you. 250 newtons. And it says the acceleration is negative 5.96. 5.96 downwards or negative. We do have a force of gravity acting. I'm going to act downwards. Hey, is gravity bigger than air resistance or smaller than air resistance? Yeah. How do you know that, Lane? Good. It's accelerating downward. I don't want you to say it's going down. It's accelerating down. Because it is possible when you're going down to still have a bigger upward force. It just would mean that you're slowing down, though. So the force of gravity is bigger than the force of air resistance. Is there ever a time when you're skydiving when the force of air resistance is bigger than gravity? Yes, there absolutely is. But when you're skydiving, you never go upwards, do you? No, you don't. But air resistance can still be bigger. Can anybody tell me when the force of air resistance is bigger than the force of gravity when you're skydiving? Right? Yeah, when you open your chute. You're going downwards at, I don't know, you're going downwards really, really, really fast. And then you pull your chute, and then you're all of a sudden going a lot slower. What had to happen during that time? You had to slow down, right? You had to slow down as you were going downwards. In order to slow down when you're going downwards, the upward force must have been bigger. So for that brief period of time while you were slowing down as you deployed your chute, the upward force of air resistance had to be bigger than the downward force. I think we talked about this a little bit here the other day. You guys remember the name Felix Baumgartner? We talked about this the other day, right? Yeah. Guy that jumped out of a balloon basically at the edge of space and free fell for, I'm not even sure how far it was, but a long, long distance. His speed ended up being somewhere in the range of 1,400 kilometers per hour downwards. That's really, really, really fast. Clearly, he couldn't hit the ground at 1,300 or 1,400 kilometers per hour, otherwise there wouldn't have been anything left of him to tell the story. So at some point, he had to slow down. At some point, the force of air resistance acting upwards on him had to be bigger than the force of gravity acting downwards on him. That's when he deployed his chute. Make sense? Yep. You have to be going at, it's about 1,000 kilometers per hour to break the sound barrier. So he was definitely going faster than the speed of sound. Having said that, there is a little bit of a, I mean, it's a big deal to cross the sound barrier, right? And he did it, not in a spacecraft. So that's a big deal. But it's not quite what it was made out to be in the press. Because you think like, oh, you get this sonic boom and he's going to, what, is he going to explode or something when he crosses the sound barrier? In the end, if there's no air, and he got going that fast because there was effectively no air up there, right? Then there is no sound. So there's no barrier to cross if there's no sound and there's no air. Does that make sense? So he's going faster than the speed of sound would be on Earth, but he doesn't have to cross any kind of barrier, you know, like a supersonic jet would have to cross, you know, if it was moving at 39,000 feet. So it's a big deal. He's going really, really fast, but it's not quite as big a deal as they made it out to be. All right, so we want to find, what do we want to find here? No, we want to find the mass, right? So let's say the net force is equal to F air plus Fg. Look, they're all a little bit different, but they're all pretty much the same. The net force is equal to the sum of the forces. The net force is also m times a. It's equal to F air plus Fg. M is unknown. A is negative 5.96. Let's simplify this a little bit here. What are we going to do with those two terms that have both m in them? We want them together, right? We want them together. Here's one of them. Here's the other one. Let's take this one over to the other side by adding. So it becomes neg 5.96 plus 9.81 times m. We get 3.85 times m there equals 250. And then we're going to say 250 divided by that is 65 kilograms. 64.9 kilograms. All right, let's take a look at those two questions, please, on 153. All right, let's take a look at number 2 here, please. This is a qualitative one, not a calculation-based question, but just one where we have to kind of understand what's going on more than actually do something. Number 2 says, during a bungee jump, the velocity of a 55-kilogram woman at the lowest point is 0, and the cord stretches to its maximum. So she's falling, she's free falling. The cord isn't stretching, and then she free falls. The cord's not stretching, then the cord begins to stretch. As she free falls, gravity is clearly bigger than the force of the cord. The cord isn't pulling at all as she's free falling. Then, as the cord starts pulling, as the cord starts stretching, the force of the cord pulling up on her becomes bigger than the force of gravity. Otherwise, she wouldn't slow down. She'd keep moving downward. She'd keep accelerating downward. So at one point, the force of the cord becomes bigger. But then she stops. When she stops, we want to analyze this question now, when she stops. What's the direction of her acceleration at the lowest point when she stops compared to the acceleration due to gravity? Well, the acceleration due to gravity is clearly downwards, right? When she stopped at that bottom point, okay, the acceleration of gravity is downward. But what's her overall acceleration? Is she accelerating downward? Is she accelerating upward at that point, or is she not accelerating at all? She's not moving, right? Who says she's accelerating downward as she stops? Who says she's accelerating upwards as she stops? Who says she's not accelerating at all as she stops? All right, it's about 50-50 then between she's not accelerating at all and she's accelerating upwards. Somebody that says she's not accelerating at all, can you give me your reasoning, your rationale? Her rate of acceleration is 0 when she stops. Why? Is your hand up? No? Anybody want to take a stab at that? Anybody that said that she wasn't accelerating at all? Here's the thing. When she stops, clearly her velocity is 0. She stopped. But acceleration doesn't measure velocity. Acceleration measures the change in velocity. As she stops, what happens the moment after she stopped? She's going down, down, down. She's slowing down, she's slowing down, she's slowing down. She stops, and then she goes up, 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 right? The cord pulls her back up. She's not moving at this point. But there is an acceleration. Her acceleration is which way as she's at the bottom point? Fraser, I know you have this because you had your hand up a second ago. The acceleration is upwards, yes. Gravity is still downwards, but she accelerates upward because she's slowing down in the downward direction, and then she speeds up in the upward direction. That's an upward acceleration. That requires an upward force to do that. Question B. I guess we already answered that. Question A, they were just looking for the fact that they're opposite. And in question B, looking for the actual direction. It's upwards. All right? I'm going to give you one more question today, and that's it, and then we'll wrap it up for the day here. It's 3.11 on 156, and it's going to look quite a bit different here. This is not an elevator problem at all. We got a 20 kilogram truck tire. I'm going to label that as 20 kilograms right there. On a horizontal frictionless surface, the tire is attached to two light ropes that pass over light frictionless pulleys with pails B and C. Pail B has a mass of 8 kilograms. Pail C has a mass of 6 kilograms. We want to find the acceleration here. All right, the step that I'm about to do is not mandatory, but I find for a lot of people it's helpful. I'm going to pretend that it's all on one plane, as opposed to, you know, this plane and this plane. I'm going to pretend that it's all on one plane. So what I'm going to do is pretend that I'm pulling the pail B up like this. Pull it up on the same plane. Pull pail C up like this. Then my diagram is going to look something like this. We've got A. We've got, sorry, that's B, I guess. We've got object B. We've got the tire A. And then we've got object C, the pail C. If we twist it up like that, then pail B experiences a force of gravity to the left. And it's 8 times 9.81. It's not really to the left, is it? It's really downwards. It's really acting down on it like this. But we're going to draw it to the left here, and you're going to see why in just a moment here. There's also a force of gravity acting on pail C. We're going to make that force of gravity to the right. We'll call that FG3, and it's going to be 6 times 9.81. It's not really to the right. It's also truly downwards. But the reason that I've drawn it like I have is to show you, to remind you, that these forces are acting in opposite directions. Look at this. Okay, it looks like in this first picture that these two forces are both pulling down, so when I go to plug them in, they're both going to be negative. But I can't do that because they're opposing each other. One of them's got to be negative and one of them is going to be positive. When I draw the diagram like this, it reminds me that one of them is negative and one of them is positive. Let's go to the next step. We know what it is, right? F net is equal to the sum of the forces. We're going to call it Fg1 plus Fg3. M times A is equal to Fg1 plus Fg3. M is, what is M? What mass do we use there for M? 8, 20, 6, or some sort of combination thereof? 20? Who agrees with 20? Who thinks we should use something else? What do you want to use then? If you don't want to use 20, what do you want to use? Yeah? How about 34? Why, Aiden? Yeah, if we're looking for the acceleration of the whole thing, we're analyzing the whole system, then let's use the whole mass, 34 kilograms. Multiply that by A. Fg1 is, we're going to say it's 8 times negative 9.81. Fg3 is 6 times positive 9.81. Are we making gravity positive? Is that what I'm saying here? This term, is gravity positive? Yeah, but why? Because it acts down. Yes, exactly. They're both downward forces. Gravity always pulls downward. There's no exception to that. Gravity always pulls downward. That's how we define down, is the way that gravity pulls. But yet we're making one negative and one positive here, as Rutger said, because they both pull the system in opposite directions. One pulls it to the left, one pulls it to the right. So it doesn't really matter which one we make negative and which one we make positive, but one of them has to be negative, one of them has to be positive. That becomes, if we do the math on the right-hand side, it becomes negative 19.62. Then we're going to say A is equal to negative 19.62 divided by 34, which is, I don't know, somewhere around 0.6. 0.58. Thank you. Negative 0.58 meters per second squared. Other than that thing that I have circled in red there, this is the same problem as we've done a million of over the last week. All right, your homework for tonight, and during scheduled help, if you're going to stick around here, is the practice problems on page 3.11. Sorry, on page 156. I think they're actually on 157. Just double check that. It's the ones that go with these practice problems, but I seem to remember that they're on the next page, page 156 or 157, whichever one goes with this page. All right, that's it for today.